Two, one, you're live.
All right, I think we are good to get going here. So hello again, everybody. Thanks for joining the class. Last time we finished up line protection, really just kind of hitting the tip of the iceberg on that as a topic. There's a lot more that goes into it, but I think that's probably the case for any of this stuff, any of the topics that any of the presenters have gone over. So this is my last class today, presenting to folks. So I'm going to move on to another topic that we'll try to cover at a very high level and quickly of bus protection. So I'm going to jump right into it, and we can go over our agenda. Topics we're going to cover today. So I'll do a little bit of an introduction about power system buses, what they are, why it's important that we provide reliable protection for them. And we'll take a look at a few of the typical types of bus protection schemes. There's a whole lot of different varieties out there of how you can protect power system buses. So I wanted to cover a few of the most commonly applied ones and some of the kind of theory behind what we look at when we're trying to protect a bus. So we're going to take a look at time coordinated protection, which will be a little bit of a revisit of some of the stuff we talked about in the line protection class, because line protection is a method of protecting power system buses. And then we'll take a little bit deeper dive into differential protection schemes, and we'll touch on differentially connected overcurrent, percentage restrained overcurrent, and then high impedance bus differential protection. We'll wrap it up with a high impedance differential calculation example, assuming we have time. I've been going over on every other one of these, so we'll see. If not, it's in the notes, and there's some good information in the relay instruction manual. I borrowed the example from that you can always go and do some more investigation if you're interested. And then I've also attached a few references and kind of continue reading as folks have more interest in this. There's a lot of good industry information out there. So as usual, just jump right in and let me know if you've got a question on anything as I'm wrapping up a topic, or as I'm going through things, if you need a little bit more clarification, that's just let me know. So buses act as a connection point between all the other power system equipment. So typically your bus might have a variety of lines, transformers, capacitor banks, reactor banks, other specialized equipment connecting to it through breakers. And there's a lot of different bus arrangements and station configurations that use buses in different ways for different purposes. But in general, everything's there to connect the different parts of the power system at the substation or switching station. So I've got a fairly simple bus application over here where we've got 5 breakers connected to the buswork, and each of those breakers would, these arrows would represent another piece of power system equipment. So it could be a transformer, a line, cap bank, any of that stuff. So this is a straight bus configuration where you've just got a bus acting as a node, and then there's a bunch of breakers coming off of it to feed whatever the purpose is. And there's a bunch of other bus configurations that are used for various reasons, but we'll really focus on this simple bus arrangement for the protection topics we're talking about. So bus faults, if you have a fault on a bus, for a line, typically be tripping the breakers at both ends of the line. Each line terminal has a breaker, and that's how you'd isolate the fault. Bus protection, you've got to trip every single source off the bus, because you've got to isolate any potential source of fault current to the bus zone. So really, you've got an increased need for highly reliable and high speed protection because you really don't want to misoperate your bus zone. You're tripping off not just one line, but in this case, it could be 5 transmission lines worth of worth of load and other things that could have a very big impact on your system, drop more customers, things like that, because you're dropping a lot all at once when you have a bus fault. So that comes into play when we're looking at our protection and looking at the bus protection needs and requirements of a certain system. We really got to take a look and put some effort into making a highly secure and dependable protection scheme. Typically, it's got to operate very fast, and we've got some other considerations that would go in there that align with the other general protection system considerations that we talked about over the last few classes. So you typically apply a dedicated bus relay for most buses these days. There's a lot that use remote protection. We'll talk about here in a bit. And the bus zone, as we discussed with the line, is defined by the CTs on the breakers that are monitoring currents into the bus. So we've got the kind of dash box here that shows the typical bus protection zone for most schemes. If you do have a bus protection operation, typically you're going to operate a bus lockout relay that will provide tripping and block closing of all these breakers. And what that does, and I don't know if you talked about lockouts in any of your other any other classes, but basically it's like a control switch handle at the station that is operated by the trip signal from the relay. It trips and then prevents you from closing the breakers back in until someone actually goes to the substation to reset the lockout handle and then restore the site. And that's done because typically if you've got a bus fault, it's a pretty big deal. You don't necessarily want to close the system back into that fault. Obviously something's gone wrong with the bus or the relaying or something that warrants sending someone out to the site to investigate prior to making a decision to close the bus back in. So typically, most substation equipment, if you determine that you think that there's a fault with the equipment itself, it's going to operate a lockout relay to do the similar function. Get somebody out to the site and see what's going on prior to trying to restore that equipment. Where a line is a lot more likely to have a temporary or transient fault, like a lightning strike or something like that. That once the breakers clear, you've got you can close it back in and at least try to restore it through automatic reclosing or manual closing. You don't really want to do that typically for a bus, though I've seen utilities do that in the past for some buses. So as I mentioned, I include this slide in every single presentation I do on a protection topic because as protection engineers, we really do want to focus on these as considerations and objectives of what we're trying to accomplish, and be able to describe the schemes that we're applying in these terms. So we've got reliability, which is the assurance the protection scheme will operate properly or correctly. And that's broken up into dependability and security, with dependability being the degree of certainty it will operate correctly. So it will trip for any real fault condition, and security being the degree of certainty that it will not operate incorrectly. And ideally, when we're designing a protection scheme, we're finding the right balance between those two key components. Additionally, we want selectivity. So we want to minimize the impact of service continuity and disconnection of equipment for a fault. Selectivity is important for everything, but for a bus fault, you're really going to have to trip a lot anyway, but you don't want to trip any more than you have to. Speed. So we're going to try to clear the fault as fast as we can. For some lower voltages, time delay clearing is acceptable. For transmission, 115 kV and above type voltage levels, typically we're looking for something that's going to operate fairly instantaneously, similar to the line protection, where the relay will detect and operate for the fault in a cycle or less, electrical cycle, and then your breakers will clear in 2 to 3 cycles. So all in from the fault starting to the fault being cleared, we're talking about 4 or 5 electrical cycles. So a small fraction of a second for clearing times. Simplicity. So we want to be able to accomplish our scheme with the minimum amount of equipment and the simplest and most straightforward approach to meeting the rest of these objectives. And then economics. And economics comes into play with bus protection because if you're providing a dedicated scheme, it uses a lot of CTs. You get a lot of cabling. You might have more expensive relay to apply the scheme, or some other engineering considerations that go into it. But as with everything, economics has a role in what we're trying to accomplish. So the first type of bus protection scheme we're gonna talk about is a time coordinated protection. So this is in general the use of local or remote overreaching elements. We talked about overreaching elements with the line protection discussion. Elements that look past their intended primary zone of protection, or the equipment they're trying to protect. We'd use those with a time delay to coordinate with other protection, typically on distribution buses. So this could be a 12 kV bus or a 4 kV bus, something like that is where you most commonly see this approach applied, though I've certainly seen it applied at higher voltages as well. New installations, typically, utilities are investing in a more advanced and more costly bus protection scheme, even at those lower voltages. I've started to see a trend where utilities are, putting dedicated bus relay even at the distribution voltage levels. So you don't typically see this type of protection at transmission substations anymore. At that point, they're definitely investing in a more robust bus protection package. So this can kind of come in a couple different varieties, but the general idea is that you've got either other relaying throughout the system, or relays at the at your station that would operate to clear a bus fault. So in this distribution example here, we've got a transformer. It's got a high side fuse. It's got a breaker on the low side that might have a time delayed overcurrent element, a phaser ground, or maybe both overcurrent protection on that. And that would back up faults on the feeders and would also respond for a fault on a bus. Because it has to provide coordination with the feeder protection, it has to be slowed down, pretty significantly to provide coordination and have time coordination between, the relay at this T breaker location and the relay at the F breaker. The other thing this would typically do is thermally protect the transformer. That's really its main objective, would be to prevent the transformer from damage from through faults. So the fact that it also protects the bus is kind of a backup point for that. So this is one example of that time coordinated protection for a bus. Another one would be the transmission protection that we talked about over the last couple of classes. We talked about having a step distance scheme with time delayed zone 2 elements that would see past the next bus. So that's another example of how we would, how you could protect a bus with this time coordinated protection. So if you had a bus with 3 transmission lines coming into it, they all had zone 2 elements that overreached the bus because that's how we configure those elements. You could protect the bus with that remote equipment. And it would, clear the fault. It would trip off all the lines, but the fault would get cleared, and it would be after whatever the zone 2 time delay was to clear that bus fault. So a couple advantages of this type of scheme: it's inexpensive. You don't have to buy a dedicated relay. You don't have to buy extra CT sets on your breakers. You can use the other equipment you've already purchased for other functions to provide some level of bus protection. So that's really the main advantage. Another advantage would be, in the case of that transmission example, if you're using remote relays that aren't even at the same station, you can, still provide protection even if you have a major failure. If you're, DC systems or other systems at this station, you've still got that remote backup, remote overreaching element that should clear the fault. The main disadvantage of it is, it's slow. It's not very selective because you're waiting for whatever elements will see the fault to clear it. So you may be tripping potentially more than you need to for a time coordinated protection like this. And it requires you to do some analysis and a lot of simulations to make sure that the coordination that you're providing, the coordination between the time over current elements here, the distance elements in the transmission system, whatever elements you're using, you've got to make sure that they are set to coordinate with the other protection around them to make sure that that you're having the best selectivity and coordination that you can. So, this is certainly an option, as I said, but it's not maybe the preferred option for most bus protection applications. Really what we see most commonly these days on bus protection is a differential scheme. So we touched very briefly on differential protection when we're talking about pilot protections. You can protect a transmission line differentially as well. But we'll do a little bit deeper dive into that today on the bus protection, the bus protection topic. So the basic premise of differential protection in any variety is that you're summing all of the currents in and out of a piece of equipment, in this case a bus, and you take the sum of those currents and use that as the operate quantity for your relay. So in effect, what you're doing is you're taking Kirchhoff's current law, that the sum of all currents entering or exiting a node must equal 0, and you're applying that to the relay. So you would do it per phase. So you've got a 3-phase system. If you've got phase labels A, B, and C, or 1, 2, and 3, each one of the phases would have its own summation. So you're not summing between, you're not summing all 3 phases together like you would to get a 0 sequence quantity. But you'd apply this differential summation to each phase, and then apply that to a relay that would monitor that differential current. In normal operating mode, whether it's load or an external fault, all of those currents should sum up to 0. And if you have an internal fault, they're not going to. So you've got that as an operate quantity that you can use. There's a couple different methods you can do to sum the currents. So the historical way of doing it, and it's still applied this way in some types of applications, including one of the ones we're going to go over, or a couple of them we're going to go over today, is to just wire the CT secondary circuits together. So take all of the phase A CTs from each of these breakers and wire them in parallel with one another. And the resulting current that you wire into the relay, also in parallel with those CTs, will sum up to the sum of the currents entering the bus and exiting the bus. So that was very typically done in a lot of historical applications using electromechanical relays and things like that. But with modern relays, you've got some other options. And the primary one we see with modern percent restrained differential relays is to wire each set of CTs to the relay individually, and then have the relay map those CTs together to do the summation in the math inside the relay logic. So it's got an algorithm that goes in and will take the vector sum of all of the phase A currents and calculate that into an operate quantity. So any of these differential type schemes are going to have this similar type of operation. So you've got this IOP quantity, which would be the current going into this, in this case, an overcurrent element. And that operate quantity, the differential operate quantity, during load is going to be 0 amps, because everything is going to sum together, and the currents in the bus are going to cancel out into the bus, are going to cancel the currents going out of the bus. Same thing for an external fault. So during an external fault, it's the same premise, just at a higher magnitude. So if you had a fault on whatever was connected to this leftmost breaker, you're going to have fault current contributions coming into the bus on the other 3 breakers, and all of that's the primary current is going to sum together and is going to be exiting the bus over the over that first kind of left-hand breaker there. So during an internal fault, you're summing up, and you're basically summing up the fault current. You now get a current path that's not accounted for with your CT connections, and they'll sum up to the magnitude and current and angle of the fault current at that bus. So we talked a little bit about what makes a good operate quantity when we were talking about distance protection. We looked at during load, you've got an impedance that's got a certain angle and a certain magnitude you can expect, and during a fault that changes. Your angle moves closer to the line impedance angle, and your magnitude decreases significantly based on the measurements you're taking. So that's what made it a good operate quantity that we can make a informed protection decision with. Differentials, probably one of the best when it comes to that, because you can see here during normal operation or a fault that we don't want the differential scheme to operate for, we are going to be somewhere very near 0 amps of operate signal. And then for an internal fault, we're going to have a very large fault current, or whatever the fault current is. It's we're going to be seeing that. So you've got a very big difference in what you see during non-fault and not internal fault, and an actual fault condition you want the relay to operate, which makes differential protection a really popular choice for protection engineers whenever we can justify the expense of all these extra CTs and wiring and some of the complexities that come with that. So from that we can say, okay, this is a really great choice for our protection, but there are a couple challenges with it. Differential protection is generally pretty sensitive to CT accuracy issues. So, any of these current transformers on the circuits, I don't know if anyone else has gone over CT performance in any of the other, past classes, but, the CTs aren't ideal for a full range of currents. Like any transformer, we're trying to, step down at a a current through a ratio. And that the CTs are designed to operate for a certain magnitude of current and a certain amount of load or burden connected to the CTs. And if they go outside of that range, they will start, they'll start to perform less accurately. They'll saturate, the CTs will saturate, and the secondary current will no longer be directly proportional to the primary current. So if you start having that happen, for an external fault condition or some other reason, the current, the operate current is going to reflect that. So that's one of the things we've got to look at and we've got to plan for with our protection, our bus differential protection. One of the other challenges is that it does require dedicated CTs. So most bus protection schemes are applied that the only thing connecting to those CTs is the bus differential relay. And the more breakers and other things you have connected to your bus, the more CTs you're going to need, the more CT cables you're going to need, which really drives that that cost impact of applying this type of scheme. So the first type of differential scheme we're going to talk about is a differentially connected overcurrent scheme. It's the same figure that I've had up here for a while. So basically, you sum together the CTs, and this is typically applied with CT secondary circuits summed together, though you could theoretically apply it if you're doing digital summation within a more modern relay, though I think most of the time you would be if you're doing that, you'd use a more advanced scheme, like the percent restrained differential that we'll talk about next. But basically, sum together all those CTs and your operate current will come out of those. So again, it's going to be 0 amps or near there when you have a, not a bus fault condition, whether it's load or an external fault. And then you'll have the fault magnitude on there when you have an internal fault. And that just gets connected up to a very basic phase over current relay, which in some cases may be instantaneous, or you can provide a time delay, either fixed time delay or a inverse time type characteristic. And if the differential current goes above a threshold for that required amount of a time delay, the element trips, stating that there's a fault on the bus, and then the trip output of the relay would be wired to a lockout, which would trip and block close all of the breakers. So we don't see this scheme applied very often. We'd have that overcurrent element. Oftentimes we see a stabilizing impedance in parallel with the overcurrent element itself, which helps with some of the CT errors and things like that the scheme will see. But it is something that we still see used in older installations and things like that. And as recently as a couple months ago, I helped one of the engineers on my team work through a differentially connected overcurrent scheme like this. So it does have some advantages. It's generally pretty simple. The premise of the differential current goes above a certain level, you trip is very straightforward and simple. It can be high speed. If you use an instantaneous protection on there, your overcurrent elements don't take a long time to assert. So you can, this could be a scheme that you would have, that clearing of a bus fault in 4 or 5 cycles that I mentioned when we were talking about the objectives. And in general, it's fairly selective. So you're going to operate for bus faults, and you're going to operate just the required breakers when that happens. The big disadvantage with this is the security impacts of CT measurement accuracy. So as I mentioned on the last slide, your CT performance as you get higher fault higher current going through the CTs, or you have a higher burden connected to the CTs, a larger impedance connected to the CT, can cause the secondary current to no longer be proportional to the primary current. And if that happens, you start to have differential current show up for cases where you don't want them. And that can cause a misoperation of your bus protection for a fault that it shouldn't operate for. It could be a fault out on one of these lines or transformers connected to the bus. So this type of scheme was applied quite a bit, and has really not been used as much, at least in my career. So 15 to 20 years. I don't know if we've really applied a new installation of something like this directly. So that same type of scheme, we still have differential as a really viable operate quantity, but we just need to secure it against some of the limitations that we have for CT inaccuracy issues and things like that. So the idea of a percentage restraint differential came up decades ago. They had electromechanical relays that were set up in this way, and then there's a lot of different varieties of microprocessor-based relays these days that apply the same principle. But the basic idea is that when are we going to have that CT accuracy issue? When are the CTs likely to saturate? And the answer is when we have high fault currents. If we rate the CTs properly and we specify the right CTs, ideally they're not going to have any saturation issues. But if they do, it's going to happen when you have high currents running through that that CT. Which in the case of a bus, if you have an external fault, just outside of the bus on one of these connections, all of the fault current from all the other sources is going through one CT on the way out. You'd have sources coming into the bus on the other three, and those would sum together, and all of that primary current would be going through the breaker for the faulted piece of equipment external to the bus. So someone came up with the idea of let's find a method to say how much current is going in and out of the bus, and let's compare that to the operate quantity. And we can basically raise our pickup of how much operate quantity we need based on the magnitude of current going through the bus. So that was accomplished by adding a restraint element that monitors the total fault current through the bus, and then that restraint current is compared to your operate current to make a trip decision. So if you have a case where you've got very high fault currents, you're going to need more operate current to trip. And if you have very low amounts of current, which could be a load condition or a more distant fault that had a lower overall fault current going through the bus. So I've got a few calculations or equations down here. So you can see the top one, the IOP, or the operate current, is your differential current. So we're taking the vector sum of all measured currents into the bus. So this is 1, 2, and then however many breakers. So this would be, in this example here, you'd have 4 currents wired in and summed together to calculate that operate current. And because we're doing a vector sum of these, they should sum up to 0, because the angles for current going into the bus will be 180 degrees from the angles of the current going out of the bus, because all of our CTs are in the same polarity direction. They're all looking for current going into the bus. So that's our operate signal. And then we're looking at a restraint signal as well. And the restraint signal is also a sum of those currents, but in this case, we're just looking at the magnitude. And we're summing the magnitude of each of them as our as a restraint quantity, basically is looking at, how much current is going through the bus now. Doesn't matter if it cancels itself out, but how much current is going through there. So if we had this same example up here, and we've got the fault on the leftmost equipment here, external fault, and we had 1,000 amps of current coming into the bus on each of these other lines or transformers or what they are, you'd have 1,000 amps of current going in times 3 and 3,000 amps of current leaving the bus. And when you calculate as a differential quantity, because the angles of those currents cancel each other out, you're going to have that 0 amps of differential current. And the restraint current, you're going to sum them all together and just look at the magnitude. So you'd have 1,000 plus 1,000 plus 1,000 plus 3,000, 6,000 amps of restraint current. And that quantity can then be compared to the operate quantity to really secure this element quite a bit. So if you have a high current scenario where you're going to start to have some CT saturation, you're going to have to see a lot more operate current. So as you start to saturate a CT, it doesn't just drop from ideally matching or being proportional to the primary current to just not going to any, not outputting any current at all. You're going to slowly degrade the accuracy of it, and because of that, you're probably not going to have an operate current that's enough to do it, even if you start having a CT saturation condition. So there's a few advantages of this scheme. The main one is that restraint current secures the element during CT saturation, which is what I've just been talking about. Modern relays, so microprocessor-based relays where you're wiring each of these CTs into a separate input, can handle CTs with different accuracy classes, different CT ratios, different even connection types in some cases. So that can be an advantage if you're retrofitting a station and it's got a mix of CTs from different vintages on there. You can account for that with modern relays. You can set it pretty sensitive, because you've got this restraint current here. You don't have to be as concerned with that CT saturation issue. So you can set the pickup of this fairly sensitive, which is another advantage. And then, because you've secured the element, you've got high selectivity. So this really should only be operating for bus faults, and it should, it will only trip the required equipment. It's not going to see faults anywhere outside of the bus and respond to those. So, you've got selectivity advantage there as well. The main disadvantage is it's a higher cost and complexity. You've got a more expensive relay. You've got, potentially longer CT cables because they've all got to go from the CT location to the relay. But in general, those disadvantages are, offset by the advantages. So we see a lot of these types of percent restrained applications in new installations, especially in the transmission system. One other advantage with this, with the modern relays where you're wiring the CT connections in individually, is you can do some more advanced stuff because the relay has multiple elements. You can apply breaker failure or overcurrent protection, backup elements within that same relay. Very advanced schemes. If you've got, multiple buses tied together by switches or breakers, you can reconfigure the bus zone based on what breakers are closed in at that time. So you can do some more advanced stuff with the more modern relays, with this type of scheme. So if we take a look at, what is my operating restraint current going to look like during typical conditions? we can kind of go through that. And as we're kind of thinking about this, you can see some of these typical percent restraint characteristics over here. So that I think it was G quantity here would be typically set as a percentage. So for the last one I said, I think is set at 60%. So if your operate current is greater than 60% of your restraint current, that's when you trim. So we can plot that as a line with a slope plotted with operate current versus restraint current. You can see we've got a kind of base level pickup that I don't want this to operate below this quantity at all. Just not, no matter what, the operate current has to be above this level, this pickup level, before you make a trip decision. And then the slope or the percentage defines how much operate current you have to see versus the restraint. So this top one's a pretty typical one, a very basic single slope characteristic. Some relays have a dual slope characteristic that as you get more restraining current, you switch to a higher percentage, so that you have to see more operating current to further secure this in cases where you've got high currents and a larger potential for CT saturation. And others might have some kind of an adaptive slope that starts one way and then gradually moves to a different type of characteristic. So if we take a look at what's going on with this operate and restraint current during different conditions, I kind of gave a very basic example on the last slide, but during normal operation with load current, your operate signal is going to be zero because currents in and out of the bus are going to sum up to zero based on Kirchhoff's current law. And your restraint quantity is going to be twice your load current because you're going to see the load current going into the bus and then you're going to see it going back out of the bus. One thing to note with this is one method of calculating a restraint current. Different relays use different things. I've seen some that have a factor of 1/2 in front of them. So that your restraint current during load would be your load current. I've seen others that do other types of calculations to so understanding how your restraint current is calculated is important. But I left this one in here. This is what Schweitzer uses for their 487B relay, which is their percent restrained differential bus relay. So for an external fault with no CT saturation, so all the CTs are accurately reflecting the primary current or stepping down the primary current, it's the same thing. You're going to have 0 amps of current in your operate, and you're going to have 2 times your fault current because you're going to see the fault current coming into the bus and then leaving the bus, which is why you end up with that 2 times factor. And then during external fault, you may have saturation. Again, one of the CTs, the CT closest to the equipment with the fault, is going to be seeing a high magnitude of current and may start to saturate. So depending on how much error that saturation is causing is going to drive what your operate current is. But your operate current is in general not going to be 0 because you're going to have that error current based on your CT accuracy being degraded by the saturation of the core of the CT current transformer. But in that case, your restraint current is still going to be larger than your fault current, because even if that CT was fully saturated and was putting out 0 amps of secondary current, which is unlikely, you're still going to be monitoring the all of the other currents into that bus. So you'll still have a reasonable restraint quantity that you can rely upon to secure the element. And then during internal fault, your operate and restraint quantity are going to be both roughly equal to the fault current. So your CTs are going to sum up to the fault current with the differential calculation, and then the magnitude summing together should roughly equal the fault current as well. So, that's equivalent to that 100% factor here. So as long as your slope is set less than 100%, the relay would operate. Typically, they don't let you set it that high. So you're usually in that 60 to 80% range is what you typically expect to see for your for the slope characteristic here if you're using a single slope. So I guess any questions on the stuff I've gone over so far? Again, I'm covering a lot of ground on this, but it's trying to get some exposure to some of the different options out there. All right, well, we're going to move on to high impedance differential, which is the last type of bus differential protection that we're going to cover. It operates on a fairly different principle of how you set the relay and the operate quantity that you're looking at. So in your other the percent restrained differential or the differentially connected overcurrent, you're looking at a current as your operate quantity, and in general you're trying to reduce the burden connected to the CTs to prevent them from saturating, from having that CT performance and accuracy issue. A high impedance scheme works with a different principle. You sum your CTs together, the CT circuits, the secondary circuits together to create that differential current. And then rather than connecting it up to an overcurrent relay or something similar, you are connecting it to a high impedance stabilizing resistance. So you'll have this stabilizing resistor here that might be 2,000 to 3,000 ohms that is going to be seen, and it's going to be the burden connected to the CTs when there is a differential current present. And rather than operating on current, you're going to operate on voltage. So if the voltage measured across that impedance is higher than a threshold, that's how you're going to make your trip decision. Typically, you'll see that these would have an MOV to help clamp the voltage. So if you get a high amount of current dropping over this resistor, you'll end up with a large voltage that will be seen by the relay. And for safety reasons and equipment protection reasons, you might want to clamp that voltage down. It doesn't have to be 1,000 volts across the resistor. It just has to be above whatever that set point is. So adding the MOV adds some protection for the equipment and also makes it a little bit safer for personnel working in the relay and on a cabinet. Another thing you'll typically see is that there'll be a lockout relay contact that will close to short out the current path through that stabilizing resistance, the MOV and the voltage element once the relay makes a trip decision. And that's there just to remove that part of the circuit if once the trip decision's been made. Someone's then going to have to go to the site to reset that lockout relay and operate and allow the system to be restored. Many modern relays also include an overcurrent element that can be used if this overvoltage element, the high impedance element, is disabled for whatever reason, or after it trips, that overcurrent element can be used to detect a breaker failure, or if you have to bypass one of your breakers and turn off the differential protection, you can use that time or instantaneous overcurrent element in this relay to provide some other protection functions. So the main advantage of this type of scheme is that it has very, very high sensitivity. It's highly selective and it's very high speed. It's one of the fastest bus protection options out there. So it's got a lot going for it. It does have some disadvantages. Because you're summing the CTs externally and using the CT performance and saturation performance and how it responds. Generally you need CTs with the same ratings, and you certainly need CTs with matching ratios. So you can't have a 2000 to 5 amp CT on CT1 here, and then have 2, 3, and 4 be 1200 to 5. You're not able to do that with this type of scheme. And additionally, because when the relay sees a fault, there's a high likelihood you're going to be saturating your CTs over this resistance. The CTs have to be dedicated and only used for this relay, with the percent restrained differential element or differential protection or other similar protection schemes. You may be able to share the CTs and use one CT to do a breaker failure relay as well as the bus relay, or some other type of protection. You can wire multiple things into that same CT circuit. You don't really have that option with a high impedance scheme, because when there's a fault, when there's a bus fault, the CTs aren't going to perform, likely going to perform the way you want them to for that other relay. And you're really trying to minimize any variations in the burden connected to these CTs, so that you can accurately calculate the high impedance protection settings. So with this scheme, looking at the same stuff we looked at with the other ones of, what is this relay seeing with a during load, or an external fault, or a fault with a saturation, or an internal fault. It gets a little bit more complicated, because you really have to look at the performance of the CTs themselves. The figure on the bottom here, if we look at from this RCT to the left, that's a rough approximation of the equivalent circuit for a current transformer. That's how we'd model it. RCT being the current CT's internal winding resistance, and this XM path here being the magnetizing impedance of the CT. And you can see it's shown, roughly drawn here, as a nonlinear impedance. And that's where that accuracy comes from. We'll look at a excitation curve in one of the future slides, but basically that nonlinear impedance means the error current is going through that path is going to stay linear for some amount of time, but then as you hit saturation, more and more current is going to be going through this magnetizing branch rather than through the circuit. So for this example we have here, you can see, we've got our 87Z element. So this is the voltage measurement element. It's actually measuring current, but then the relay calculates that into a voltage to do the actual set point. And here's our RS, which is that stabilizing resistance. And for a load condition, we've got in this case here, the transformer, feeding some circuits. We've got all of our current going into the bus on one set of CTs, and then all of the current going out of the bus on additional CTs. So this right-hand portion of the circuit is the current going into the bus, and the left-hand circuit is the current going out of the bus. And you can see we've got n-1 here. So the number of CTs -1 is our quantity there, and same thing, with any of this. So the basic idea is that the current going into the bus here on the right should be equal to the current going out of the bus, the summation of all of those currents. This is kind of a lumped aggregate equivalent of all of the currents going out on this side. And because I1 equals I2 in that case, we have no or very little current flowing through this stabilizing resistance. So we're not going to get a very high voltage or any voltage at all through that path. So with load or external fault with no saturation, we're going to be seeing nearly 0 amps through that path, and we're going to see almost no voltage, which is our operating quantity. We've got kind of a graph here where it's showing, okay, yeah, our measured voltage, our operating quantities here is very low, and we'd be looking for a couple hundred volts for our pickup setting. So the next case we'll look at is what happens during external fault if we do have saturation. And this is really what we use to calculate the pickup of the element, of that voltage element. So in an absolute worst case scenario, we don't have any current contribution from the CT that's feeding the external fault. So this feeder CT here, we're not going to have any current contribution at all from that. And that's a very extreme worst case scenario, but that's kind of what we want to think about, because it's very hard to say exactly how much saturation and what the performance is going to look like. So you can see the right-hand side of this equation here for the faulted phase. Instead of having a current source and the magnetizing branch of the CT, we've just shorted it out. And we've got our fault current flowing through that part of the circuit. And that's flowing through RL, which is the CT lead resistance. So these are the cables and wires between the CT and the summation point where we sum together all the CT circuits. And we've got RCT, which is the winding resistance of the CT, which would still be seen in this case. So we can calculate what the voltage that the relay will see for this extreme worst case saturation as the fault current times those two, or this is fault current in secondary, but it's times the two resistance values or impedance values here for the leads and the CT itself. And that's going to be a scenario we don't want this to operate for. But that's an important factor to understand, because if we understand that this is the absolute worst case is, this level of VR, we know, okay, we can set a pickup above that. And then we know we're not going to operate for an external fault, even if it's the absolute worst case CT performance that we can expect. And we see here, we've got the VR and it's set something like 120, 130 volts with our pickups selected at 200 volts. So next we'll look at our internal fault case. So during an internal fault, all the currents are flowing into the bus. The CTs are trying their best to drive a representative fault, secondary fault current through that high impedance element here, the stabilizing resistance RS. So we're going to have a large amount of current, or a higher amount of current going through that resistor, and that's going to drive the voltage across the voltage that we're monitoring here with this protection element. Your voltage driven by the CT isn't going to be, because you have a high burden, you've got this high impedance across your CT. It's going to be very much limited by the CT performance and the CT saturation performance of, how much voltage can these CTs, how much voltage and currents can these CTs really drive into such a large burden. So the CTs in this case are pretty much guaranteed that they are going to saturate, and saturate fairly fully because of the very, very large burden we've connected to them. CTs are generally designed to, carry a burden of, 8 ohms or less, and we're putting 2,000 across them. So they're not going to be able to, maintain that CT accuracy during this, but that's all right, because the only thing we really need is enough current flowing through that stabilizing resistance to get above the pickup. So that's the analysis we do to check sensitivity and make sure we're operating fine. And we're going to look at the CT performance parameters to tell how how much voltage can these drive before they hit that saturation issue, and make sure that that's above the pickup, because the CTs will try to drive that current. They're just not going to be able to. And we can, from the CT performance excitation curves, we can determine what voltage they should be able to produce. So probably a little bit of this is going to make a bit more sense when we go through our calculation example, which I think we're going to have time for. We got 15 minutes left, but before we jump in there, any questions on high impedance scheme before we get into the calculations? All right, we'll jump right in, and just let me know if you have any questions as we're going through this. So I'm going through a calculation example for a Schweitzer 587Z high impedance bus diff relay. And this is right at, like I plagiarized right out of the manual, this example, because it's a great example of how the relay works. So we've got some circuit parameters, and this is the typical stuff we would need to understand and be able to set this relay. We need to know what the CT type is. It's a C800 CT with a knee point voltage around 432 volts, and we'll look at what that is on a CT excitation curve in a couple of slides. We've got the ratio, and this would have to be the same, or should be the same parameters for all the CTs connected to this relay. Ideally, you wouldn't have some C800 class CTs and some C400s and different ratios. That makes it much more challenging to make this type of scheme work. We've got about 50,000 amps of fault current at the bus. We've got CT winding resistance of 0.82 ohms and a lead resistance of 0.6 ohms, and that's the cables and everything between the CT and the junction point of the where all the CTs are summed together. And typically for high impedance scheme, they might have a junction box out in the middle of the substation yard where they bring all the CT cables in, sum them together, and then have a single cable with a differential current on it going into the control house to wire to the relay. And we've got 5 circuits connected to this. So we've got a equivalent circuit here. You can see here these X quantities here are the excitation branch of the CT circuit. And we've got 4 of them on one side here and a current source. So these are our CTs for the part of the source off the bus that are not faulted. And then X5 over here would be the CT that we're assuming is fully saturated. So it's got 0 amps of current going across or being generated by that CT. So this is our faulted CT over here, the one feeding the external fault. So we can go in and we can calculate that VR, which is the voltage across the impedance element, looking at that circuit. And let's go back here real quick. So your fault current is going to be circulating. I had this on this one. Is this CT lead resistance and the CT winding resistance, and the fault current is what's driving that voltage. So this is that same equation here. We've got our CT resistance, we've got our lead resistance, we've got a factor here for the lead resistance. We use 1 for 3-phase fault and 2 for single phase to ground faults. And that's because for a ground fault, the fault current, the secondary current, is actually flowing both through the phase conductor, but then it's returning through the neutral conductor of the CT. And for a 3-phase fault, because it's balanced, you don't have that return path. So you only need to count the lead resistance once. And that whole calculated impedance or resistance value is multiplied by the fault current to come up with the voltage across that high impedance element. So you take the primary fault current and step it down through the CT ratio to get the secondary current. Use that to calculate the voltage that we'd be using as our operate quantity. So for this case, we take our 50,000 amps of fault current, get a 400 to 1 CT ratio is 2,000 to 5, so 400 to 1. We multiply it. It said this was a three-phase fault value, so we multiply it through our CT resistance, our lead resistance times 1, because we don't have to factor in the return path of the CT cable, and we calculate 178 volts as the voltage, the worst case voltage we'd expect to see for any external fault, because we've assumed that the CT has fully saturated and the other CTs haven't saturated at all. So as we do with any protection element, we want to set some margin or safety factor above the calculated value for a setting. So in this case, we know that 178 volts is the highest voltage we'll see for a condition we do not want to operate for. So we'll pick some safety factor to set our actual setting above that. So in this example, we set it at 150 or 1.5 times or 150% of the calculated VR, and that VS becomes our actual set point. So now we've got our setting here of 267 volts, and we can move on to validating that setting. So I mentioned the excitation curve of the CT and the knee point being an important quantity to look at. So I've got a equivalent circuit for the CT, and this is just a different sketch of that same circuit we had in the previous slides, where you've got your primary current, an ideal transformer, and then an ideal secondary current here. The secondary current then splits, and you've got an excitation current through that nonlinear magnetizing branch here. And you've got the actual current sent to your burden, your relay in this case, is here. So your actual secondary current is going to be the ideal current minus whatever this excitation current or error current is. And this will drive a voltage across the magnetizing branch, and also a voltage across your burden. Really, what we're looking at here is the voltage across our burden for the high impedance element. And where this is a very large burden, we're going to have a lot of excitation current error. And we're going to want to make sure that the CT is going to be able to drive enough of a voltage over here to be above that set point for a internal fault scenario. We know it's going to saturate, but let's see how much voltage we can really push through it. So if you look at this graph, this is a graph we use for CT performance calculations and analysis for any type of application that we need to evaluate a CT set point and CT performance. We've got excitation current on the bottom here. So that's this IE quantity here. So that's basically our error current. We've got the excitation voltage, which is this VE here, on the other axis. And you can see, as we drive, more primary current, your excitation voltage is going to go up, and your error current, your excitation current is going to go up. And we've got a linear region here from the bottom of the graph here. It goes very straight line up here, and that's where you're having your expected typical CT performance, so most CTs might be rated for like a 10% error, and that's, you're going to be seeing that error here because it's very proportional. As you drive more voltage, you have more excitation current losses through that magnetizing branch. But where it's linear, the percentage is going to stay pretty consistent as you go up there. Well, what happens is when you hit a certain point, you can't drive any more flux in the core of your CT. So that's where the nonlinear part of this magnetizing branch comes in, and you're going to, for a very small amount incremental change in voltage, you're going to have a very large amount of that error current or excitation current. So in general, what this tells us is, there's going to be a limit on how much voltage this CT can produce as an excitation voltage, and therefore you're going to have a certain amount of voltage you can produce as your voltage across your relay here. You will have a small voltage drop over this RS, which is the conductors and the CT impedance. But where this is such a large burden, almost all of your voltage drops happening across that stabilizing impedance, the 2,000 or 3,000 ohm impedance there. So one of the things we want to check when we're looking at this high impedance element is, how does this knee point, or where this linear stops being so linear, we call it the knee point, I guess it looks like a knee. Where is that compared to the voltage that we calculated for our VR quantity or set point? And ideally, you want to be some factor above that so that you can say, okay, when I have an internal fault, I can probably be pretty likely to assume I'm going to be somewhere in the ballpark of this knee point voltage, because that's the voltage the CTs are going to be able to drive to that circuit. So you want to check that to make sure you've got that amount of margin between your set point and your calculated VR and the performance of the CTs. So the last thing we can do once we've validated our setting like that is calculate the minimum current for this scheme to pick up. And I've got a figure over here showing the example. We've got all these excitation current branches here. We've got the current through the relay, and then we've got some amount of current that's going to be going through our MOV, and there's curves that would provide that info. The current through the resistance is going to be driven by the set point over however many ohms that resistor is. So in this case, for this relay, it's 2,000 ohms. And then the excitation current through the relay, we can get off of this graph, because we know if our set point is 200 volts or whatever, it's 260 something. We can look on this and say, okay, well, we're going to have, less than 0.1 amps of excitation current at that level. So that would be, what each of these branches would be. So that the minimum current for this to operate can be calculated with this and turned into a secondary quantity or a primary quantity through the turns ratio N here. So you can go look in the 587Z manual and see all the derivation of this. I figured I wouldn't put it all in the slides, but for this example, this calculation example, the relay can operate in as little as 214 primary amps, which is very, very sensitive compared to the 50,000 amps of fault current that we expect in this. So that's all I had for that. It's actually convenient timing because I timed this one out just about right. So I did include a few examples here. This is all the stuff I borrowed figures from and things like that, but it's a lot of really great information if you're ever working on a bus application. The IEEE guide for protective relay applications, power system buses is a great resource. There's some really great papers Schweitzer's put out on these topics. And then obviously the instruction manual for the relay is a great resource as well. So we're just about at time here. So I really appreciate everybody, all your input and feedback and questions over the last 5 classes. And it's been really fun doing this. So I appreciate Paul for the opportunity for me to come and sit in on the class here and meet with you all. So with that, I'll wrap it up unless anyone has any questions on anything I covered today or in general about life as a relay engineer or anything like that. So
I just had one question. When you were calculating the voltage set point, how did you determine the setting factor? Is it always 1.5 or where do you get that?
So it's 1.5 is a pretty good place to start. With anything with protection, there's a whole range of things you can do. You kind of have to have a lot of it comes down to your prior experience and philosophy and things you've seen over the years. And you learn that over time. Most of the manuals are going to have something like this. As a relay engineer, I'd be pretty hard pressed if Schweitzer in their example saying 1.5 is a good factor for their relay to be like, oh no, I'm going to set it at 1.2 because I know better. So usually you go with the manufacturer recommendation. But if you're in a scenario where you go and you're looking at this and you've got some low rated CTs and really high fault current, so that calculated value, the VR value, is getting really close to the knee point voltage. At that point, you might make a decision that, all right, well, maybe 1.2 or 1.25 is enough of a margin there that I can be comfortable that this is not going to operate for that external fault and kind of lower that set point because that you're running out of room for performance with the CTs for operating for an internal fault. So you could kind of adjust it based on the scenario you're at, but usually you'll start with whatever the manufacturer recommends for a margin or safety factor. And most relay manufacturers will provide some guidance on that of kind of typical settings and typical ranges for how you go about configuring the relay to operate properly, because it's obviously in their best interest to have their customers have a lot of success with their relays because it makes them go out and buy more relays. So usually they provide some level of guidance on that, but in the end, it comes down to experience in the specific scenarios and balancing act between all those factors of security and dependability and all those other protection system objectives. So great question.
Okay. Thank you.
All right, well, if there's nothing else, thank you once again to Brandon and the rest of the folks for coming, and have a great weekend. Thank you, everyone.
Thank you.
Yeah, thanks again, everybody. It was really nice meeting you over the course of these classes. So hopefully our paths will cross in industry here at some point in the future. So, all right, take care.
Thanks, Brandon.